So Gökçe Başar right now is an assistant professor at the University of North Carolina in Chapel Hill. He got his PhD degree from University of Connecticut in Stores with Gerald Dunn. He had several postdoc positions after that at Stony Brook University from 2011 until 2014, then at University of Maryland from 2014 until 2017, and he was a visiting research assistant professor at the University of Illinois in Chicago until last year. So since last year, he was an assistant professor there at Chapel Hill, and he's working on many interesting topics in high energy and nuclear physics, mathematical physics, all kinds of non-perturbative phenomena, finite temperature field theory, and apparently that field of research is expanding basically every year as far as I could keep trace of it. So with all of that, I will give the microphone to Gökçe, and please, you may start.
All right, so can everyone hear me well? Good. Okay, so, well, first of all, thanks so much, Igor, for organizing these online colloquia, and really happy to be a part of it. And so today I will talk about a major outstanding problem that spans several areas in physics, and I will then show how a new way of looking at the Feynman path integral and path integral of quantum field theory really can be utilized to solve this problem. And I will sort of be as elementary and sort of non-technical as possible, but if you want to know more about the sort of technical details and so on, don't hesitate to ask me. Or if there's anything that you want me to clarify, again, don't hesitate to ask me. And this is work I've been doing in collaboration with Andrei Alexandrov from George Washington University, Paolo Badacchi from University of Maryland, and Neil Warrington, who's right now at INT, a postdoc, and Greg Ridgway, right now he's a graduate student at MIT. Okay, so the main motivation, the sort of broad theme, is to understand the physics of strongly interacting systems, that starting from first principles. An example that I'm particularly interested in is the dynamics of quark-gluon plasma, which sort of is the phase of matter that occurs at extremely high temperatures, such as the early universe when it was roughly a microseconds old. So quark-gluon plasma is created at heavy ion collision experiments at the relativistic heavy ion collider at Brookhaven Lab and LHC at CERN. And so in these experiments, the heavy nuclei such as lead or gold are smashed with very large energies, and this collision creates a pretty wild explosion that reaches at extremely high temperatures. It's trillions of degrees, so it's or in high energy units at the scale of 100 MeV, hundreds of MeV, and this temperature is high enough to break the bonds that keeps the protons and neutrons together, and the quarks and gluons, which are the constituents of nuclei, roam free, creating this plasma. And so this is the aftermath of such a collision, and these are all the particles that are produced after the quark-gluon plasma cools down. And then, so from carefully investigating the dynamics of these, the patterns that emerge from these tracks, we try to obtain information about the early stages of this collision, where which gives us information, direct information about the dynamics of quark-gluon plasma. This is the experimental part of it. Okay, so here there's sort of an impressionistic diagram of different phases of nuclear matter at extremely high temperatures and high densities. So the heavy ion collision experiments probe this region in the phase diagram, where so initially we are here at very low temperature and some finite chemical potential. The collision sort of teleports us here, and then the system cools down. As it cools down, it passes through a crossover or a phase transition from the quark-gluon plasma phase to the hadron gas phase, where the phases basically protons and neutrons bound together. And one of the outstanding questions about this phase diagram is, for instance, whether there's a critical point that separates, which is a singular point in this phase diagram that separates a crossover and a first order phase transition. So there are certain theoretical frameworks which are based on the universal properties of the critical dynamics around this critical point. However, the location of it has to be determined from, so the location is not the universal feature, and it has to be determined by the dynamics of QCD, or the properties of QCD. So another interesting region in this phase diagram is where the temperature is low, but the density is high. So this is presumably what happens at the cores of compact stellar objects, such as neutron stars. And again, extracting the sort of equation of state of QCD in this region is still an open problem in theoretical physics. And I will explain sort of why that is the case. So one of the interesting discoveries that came out of Rick was that the quark-gluon plasma phase was a liquid as opposed to a gas that people were expecting initially. And it's a liquid with a very low viscosity. And with some, when this was sort of discovered, it made it to certain news outlets, and it was called like the perfect liquid. It was reported with some catchy headlines, such as the Rick scientists are a perfect liquid, or New York Times at 1 trillion degrees, even gold into sloshiest liquid, and a tiny droplet of early universe, and a Big Bang poured out liquid universe atom smasher hit. Needless to say, it created some splash in okay. At the same time, so if this is a perfect liquid, so one sort of obvious question is, well, what is the properties of this liquid? What's the viscosity? So what's sort of the conductivity of this plasma, and so on and so forth. These questions are not specific to nuclear or high energy physics. There are many other strongly interacting systems, such as strongly correlated electrons, which are relevant for understanding the physics of high temperature superconductors. There's extracting this, the phase diagram starting from the first principles is still an open problem in a lot of disciplines, fields. Okay, but let's get back to QCD. So well, I can say, okay, we know the underlying theory that describes the interactions between quarks and gluons. We've had it for a while, since the 70s. We put the equations on our mugs. So surely we should be able to calculate these things. The equation of state, the phase diagram, viscosity, and all that, right? So let's see what happens if we try to actually do that. And starting from the microscopic interactions between the quarks and gluons, we try to compute the equation of state or viscosity. Let's see what happens. Okay. So in quantum physics and quantum field theory, so the quark and gluons are described by fluctuating fields, and these fields take all possible values. They exhibit quantum fluctuations, and the interactions between the different fields, or the self-interactions between gluon fields and so on, that determine the correlations with these expectation values. And the physics that we're interested in are encoded in these expectation values. So for instance, the expectation value of the density of fermions at different chemical potentials would give us the equation of state, or the current correlation function from that, we can read of the conductivity and stress energy tensor correlation function at different times will lead to viscosity and so on and so forth. And this is a very nice animation which was done by Theoretical-Physics-Colloquium Weber from the University of Adelaide, and that is a movie. So this is a typical sort of profile of these fluctuations of Quark-gluon fields. And what we're interested in, what's the computation, is the expectation values of these fluctuating fields. Okay. So many years ago, Feynman told us one way to compute such expectation values. And so this was in the language of quantum mechanics, basically the sort of the probability amplitude going from point A to point B can be, which can then be used to calculate these expectation values, is given by summing over all possible paths that one can take from point A to point B, but each path is weighed by a phase which is proportional to the action of that particular field trajectory, or the particular trajectory. Yeah, right? And in quantum field theory, the idea is very similar, except we have to make certain sort of modifications to Feynman's idea. Trajectories are now the role of trajectories are played by field configurations and so on and so forth. But long story short, if you're interested in calculating such an expectation value, what we do is we span this huge space of all possible field configurations, weigh each field configuration by the phase, which is again proportional to the action of that particular field configuration, and compute the observable on that field and take a sum. So it's a weighted sum of all the possible field configurations. So we span this whole space and keep adding up, and then that's our expectation. Okay. So of course there are certain technical problems with such an expression, namely, well, what do we mean by summing over all the fields? What's this sort of? This is an infinite dimensional space, and we have to sum over all the fields and so on. And how do we actually do this computation? Right. So one answer was again provided by Kenneth Wilson in the 1970s in the context of strong interactions. This is known as lattice field theory, which I will summarize in the next couple of slides. And there are actually three key steps in lattice field theory. So the first step is that we consider field configurations not in a continuous space-time, but a discretized space-time. So so we have a lattice of space-time points, and we calculate the field configuration at each point, and which gives us a finite dimensional space. So that takes care of the summing over an infinitely dimensional field space. However, there's still this annoying phase factor, and adding phases is not a very computationally feasible thing to do in general. And the second step is to formulate the theory formulate the theory such that what we call time is a pure imaginary number. So it seems like a strange thing to do, but there's a fairly straightforward physical interpretation of considering such an imaginary time, which is that if you look at the time evolution operator, where time is a pure imaginary number, that looks like a Boltzmann factor, right? E to the minus h times tau, where tau should be identified as the inverse temperature. So by doing that, we can actually gain information about thermal physics. But remember, this was the problem that I was interested in the first place anyway. I want to understand the phases and so on at different temperatures. Okay, so these are the two steps. And the third step is called importance sampling. So the third step comes as follows. So the first two steps render this integral that we're interested in computing, this expectation value. And this integral has now evaluated over a finite dimensional space, because where n, capital N, is the number of lattice points. It's a very large number, but it's finite. After doing this imaginary time trick, now our weight is positive definite. So I don't have to deal with sort of adding phases and so on anymore. Basically, this quantity gives me the expectation value at a finite temperature. The temperature is identified as the size of the imaginary time. Okay. However, this is still a very, very, very difficult thing computationally to deal with, because this space is generally thousands, maybe millions, sort of has thousands or millions of dimensions, and we can't just do the Riemann sums and so on. It's just not feasible at all. And the third step of this program stems from the observation that not all fields are created equal. Some fields are more important than the others, and the importance can be measured by this factor, e to the minus s. Because if there is a field configuration which has a very large action, that field configuration will be penalized severely in this integral. So the third step is to focus on those fields which are important. Okay? So that's called importance sampling, or it's also known as the Monte Carlo method. So the basic idea is that instead of evaluating the sum over every single field configuration here in our space of all fields, we look at an ensemble of fields, and this ensemble is created, is structured so that it picks up the important field configurations. So in other words, this is a Markov chain of different field configurations, which is generated by a probability distribution given by this penalty factor, e to the minus s. Within this method of computing the expectation value, the expectation value is basically the average which is taken over this ensemble. And where this curly n is the number of fields in my ensemble, and as n increases more and more, my this right-hand side gets numerically closer and closer to the actual expectation value that I'm interested in computing, and the error scales as 1 over square root of curly n, the number of field configurations. Okay, and I mean, historically, this has been a very successful method in extracting directly information from strong interactions from QCD. So, of course, this important sampling step is nowadays done at supercomputers, and the basic strategy is that to take the lattice, put it on a computer, do the importance sampling, and then from this we can sort of compute hadronic spectrum, the masses of different excitations directly from QCD. We can have a look inside the proton and see what the sort of the gluonic field configurations look like. We can obtain the equation of state for different temperatures. This is the energy density as a function of temperature, for instance, but only at very small densities, very small chemical potentials. I'll come to that. Okay. At the same time, there is the big range, big class of problems where this action S, which goes into the importance measure, is a complex number. Therefore, I can't view e to the minus s as a probability distribution anymore. So what are these theories? Most theories with finite density, for instance, Hubbard model from half-filling, QCD at non-zero density, and so on and so forth. There are dynamical problems that involve evolution in real time, and these are the problems that I need to tackle if I'm interested in transport phenomena or out of equilibrium physics and so on and so forth. And there are many other examples that I won't go into. Okay, so then what happens when the action is complex? Well, this is sort of what happens, right? Suppose, let me just give the simplest example that I could come up, where this is not a path integral, this is a one-dimensional integral with a Gaussian. So it's I know exactly what this number is, but suppose for purposes of illustration, suppose I try to compute this integral numerically. So there's a fast oscillating imaginary part here, and the integrand looks like this. Sort of, it's a very wildly oscillating function. And if you look at the scale here, it's 10 to the 191, and which means that if I try to do the sum numerically, I have to add and subtract numbers that are at the order 191. So I had plus 10 to the 191 minus 10 to the 191 and so on and so forth, so on and so forth. At the end of the day, I get something at order 1, which means I have to calculate these numbers so precisely that I'm sensitive to that tiny little difference. And this is most certainly not a feasible thing to do at all. This is actually a quite ridiculous thing to do. Okay. So another way to put this in the language that'll be more relevant for the rest of the talk is that so the problem was that I can't really view e to the minus s as a probability distribution because s is a complex number. But you can say, well, okay, the s is a real part and an imaginary part. Take the real part and consider e to the minus the real part of s. So the notation is if I put an r here that denotes the real part, and when I put an I, it denotes the imaginary part of the action. So then I can, again, play the same game, generate an ensemble of fields which are sampled with this new probability distribution, and what the remaining part, the phase, is absorbed into the physical observable that I'm averaging over, and then this expectation value that I'm interested in computing can be written as a ratio of these two expectation values. But at the same time, if you look at this, the denominator here, you can show that the magnitude of this factor grows, goes to 0 exponentially fast with the volume of space and the inverse temperature. Which means if I'm interested in going to larger volumes or smaller temperature, I need to resolve this factor, which is exponentially small, to an exponential accuracy. But I also told you that my error in this important sampling approach improves by 1 over the square root of number of field configurations. So in order to be able to exponentially resolve such quantities, I need exponentially large resources. So exponentially large resources means exponentially large computing power, maybe time, grant money, whatever. And again, this is not a feasible thing to do. So this is basically another way of saying that I end up adding and subtracting numbers that are at the order of 10 to the 191 and be sensitive to that tiny little difference. And this is typically what happens if I try to play the same game for systems which are at finite density or out of equilibrium physics and so on and so forth. So need something new, not just sort of computationally, but conceptually new. So this is called the sign problem because of adding and subtracting these numbers that change in sign. And this has been a sort of a severe obstacle in the field for a very long period of time. So there are different ways to approach the sign problem, which I will not talk about, but I will talk about another way that me and my collaborators have been working on for some time. So the idea goes as follows. So this was let me go back to my example. This was this horrific example that I couldn't deal with. The key idea is as follows. So let me go back to my undergraduate days and view this integral as a contour integral over a complex plane. So this real line where the problem is originally defined as a contour in complex plane. And from Cauchy's theorem, I know that I can actually change this contour to something, for instance, like that, without actually changing the value of the integral. So I'm not changing sort of the physics, quote unquote, but just changing how I'm evaluating the path integral, or in this case, just this integral. But if I now look at how the integrand changes on this contour, it actually behaves much better. I still have like big fluctuations and so on, and not nearly as bad as this one. Or I can go to something like this, the blue line here. The integrand is much better. So this I can work with actually numerically, right? So just the big step from one-dimensional integrals to quantum field theory is that, so I want to do the same thing in quantum field theory, not in a one-dimensional Gaussian, but an strongly interacting quantum field theory. And the idea is that to deform the path integral, quantum field theory path integral domain, the domain of the path integral to a better one in complex space without changing the physics or anything. But in this new space, so find the new domain such that the sign problem is milder. And there's a review article that's coming soon this summer. This idea originated in around 2012 by Christopher Di Lorenzo, Scorzato, and collaborators, and has been worked on by different groups. And the mathematical origins of this new idea is known as a Picard-Lefschetz theory. So it's a complex version of what's known as a Morse theory. It basically formalizes what types of new domains that I can find in my quantum field theory, such that on the path integral evaluated at the new domain is equal to the path integral evaluated at the original path integral. So what are the possible deformations of the path integral domain that I can work with? So, but I won't talk much about the mathematical part of it. Okay, so let me just in figures explain how I find such alternative domains over which the sign problem is better. So this is not a unique way of doing it. I will talk about that. There might be other domains where the sign problem is better and so on, but this is one example. Okay, so I have two conditions that I have to satisfy. The first condition is that the path integral or this deformed domain, which I will call M. So that's the analog of this, the green line and the blue line and the Gaussian. So the path integral on M has to be equal to the original path integral. So originally, typically I have n-dimensional real space. I can always put it in that form. So I will call this an allowed deformation. So this has to be this has to be the case so that I don't change anything physically. Okay, And the second criterion is that the sign problem on M has to be much milder than the sign problem on the original domain, so that there's actually some utility in what I'm doing. So without going into the technical details, let me just describe how I do this deformation. So the idea basically is this. I create this deformation through a form of an equation of motion that moves these field configurations in complex plane. So this equation of motion is called holomorphic gradient flow. I will just simply call it flow. It's a mouthful. The idea is as follows. I introduce a new parameter tau. So this tau has nothing to do with the time or the Euclidean time or the sort of pure imaginary time that I talked earlier and so on. This is a purely new sort of artificial parameter that I use to parameterize the deformation. Okay, and I introduce an equation of motion. So the speed, as you wish, that the field gets deformed is, or well, this is a complex number now, but the rate of change is proportional to the gradient of the action complex conjugated. So this bar is complex conjugate. So that's why it's a holomorphic gradient flow, because I extend now my action into a holomorphic function of the field configuration. And I just follow this. So this is a first order differential equation. So it defines a trajectory given an initial condition. And the initial condition is that my field lies in the original field space. And then I flow by some fixed amount of time. That also will be a parameter. Okay. So if I do that, this field will, my initial field will move somewhere in the complex plane. So I do that for all the fields. And then the field that's spanned by all the flowed fields will be my M. So you can show that by doing so, indeed, the path integral on this new surface, new domain, is equal to the path integral over the old domain, provided that there are provided that I don't go through any residues and so on in field space, which I will assume so far. And it's also possible to show that the sign problem on this new surface is actually much smaller than the sign problem, the original sign problem. Well, I won't explain why, but if you ask me, I will. But it's fairly straightforward to show these two criteria. Okay, so now what's the strategy? So the strategy is to discretize the field space, do this deformation, and then do the important sampling on the deformed surface. So that's what we did. This is an actual screenshot of my laptop doing the important sampling, and I will show some results obtained through this strategy, which involve both dynamics and finite density, so physics. Okay. So let me start with real-time dynamics, because this has actually the most severe sign problem that one can imagine. So again, if I'm interested in the physics of transport, viscosities, conductivities, and so on, or out of equilibrium physics, where I have a system which is in thermal equilibrium, I poke it with a stick and see how the system equilibrates back. I need to be able to compute such expectation values where this time is really real Minkowski time, okay? Because the system is actually evolving in time. So I can't do this Euclidean trick where I take time to be a pure imaginary number, because things actually do depend on real time. So weight is actually the original weight of the path integral, and of course this factor e to the is leads to all sorts of interesting things in quantum physics, such as interference and so on. But in this context, it leads to the ultimate sign problem. So remember that quantity that I introduced, the average of the phase of this imaginary part, and it was very small. It was exponentially small, and because it was exponentially small, it needed sort of exponentially good resolution. In this case, it's actually zero. It's exactly zero. That's why the real-time problem has the ultimate sign problem. I can like not only exponentially large resources, if I waited till the end of the universe, or I still won't get anything in this case. Okay. Then with this strategy that I described, it is possible to ameliorate the sign problem so that one can actually do the important sampling and obtain results. So I will show an example that we studied in these papers. So this is a two-dimensional quantum field theory, interacting quantum field theory. So it's a bosonic system with a 5⁴ interaction. Here I plot the time-dependent correlation function. So this is sort of the baby version of the correlation function that would lead to conductivity and viscosity and so on. But in this case, it's a real scalar field. So I don't have a constant charge like U1 and so on. But again, this is the analog of the object. So here, on the left and right, I plot two different momentum modes of this correlation function. And so I did a Fourier transform in space, and these are the two momentum modes, and the x-axis here is the time separation between these two operators here. So here I just plot the result of this correlation function for a free theory. So this I saw on paper, and this will be a benchmark to check the computations. So for weak coupling, I can do perturbation theory. So this is the perturbative result, again, I do on paper. And then I run this whole flow and deformation and Monte Carlo and so on. And this is the exact result that I get. And so it agrees with the perturbative calculation. And this was just a sanity check to make sure that I'm not doing something crazy. Okay. So now let's crank up the coupling. This is the strong coupling limit. Again, free theory. Now the first order perturbation theory is way off. So we are outside of the perturbative domain. Second order is way off. So there is no reliable tool in this case that I can use to calculate this correlation function. Again, then I run this whole flow machinery, and I get the exact result. So to my knowledge, this is one of the first examples where such a correlation function is calculated from first principle for large enough times. For small enough times, there are other methods that one can use, but directly from the lattice with large times, this is the case. So still, this is quite exponentially costly to do a sort of a standard metropolis algorithm. And there are several reasons for that, but the main reason, well, one of the main reasons is that when we deform this space to the flow domain, sampling this new domain becomes costly, and there's a law of autocorrelation. So it takes many steps to from one field configuration to the other to find the decorrelated step. So we actually used a more improved algorithm to generate the plots that I showed. I'm not going to go into details of that, but this is a typical. This is a plot that shows sort of the evolution of an average, so expectation value. So this is a sort of the same correlation function, but evaluated at the same time point. And on the right-hand side, this is basically the Monte Carlo time. So this shows how this correlation function is changing as I go through my ensemble, and you can see that these are like fairly correlated. So I need a lot of steps to find the correlated configuration, which of course means that I need to run very long computations to collect enough statistics to get an accurate enough answer. Okay, so one method to deal with such sort of landscape problem is known as hybrid Monte Carlo. Again, I'm not going to go through the details of what hybrid Monte Carlo is, but the main idea is that going from point Z to Z prime on this the form domain. So I introduce a sort of a fictitious momentum that sort of kicks the field configuration with some amount, and this momentum is chosen again randomly, and I follow the equation of motion, but on a constrained surface, because I'm not allowed to go outside of this space to go from point A to point B in my field space. Okay, so this is still work in progress, so I'm not going to tell much about the technical parts of it, but the preliminary results show that if I sort of run the same amount of same number of configurations with the HMC algorithm, it's actually much better. So in fact, compared to the algorithm that we used to generate the previous plots, it's roughly 40 times faster. But again, it's still work in progress, and there was also previous work by the Japanese group that used hybrid Monte Carlo, but in a finite density system, not real time. Again, some preliminary results. So this is a quantum mechanical system, but with again a quartic interaction, and with hybrid Monte Carlo, we can actually go to larger time extents that we were able to go in the past. Again, preliminary work in progress, but so far it's promising, and this is the error. So there are error bars here which are very small as I zoomed in. Yeah. Okay, so let me jump onto another field, which is many-body physics or finite density. So my example here is something called a Turing model. Well, a Turing model is a model that describes interacting fermions on a line. So it's you can view it as some form of spin chain, and it's at finite density, and the interactions are given by a 4-fermion coupling like this. So I can integrate out the fermion fields, and the Hubbard-Stratonovich field I get is, because it's like a it's a current coupling here, is a vector, and it sort of looks like a gauge field, even though it's sort of, it doesn't have its dynamics, but it's a nice prototype for QCD. It's asymptotically free. There's a sign problem at finite density, and it's some it can also be viewed as a 2-dimensional cousin of the Hubbard model. So here I show two plots. So the plot on the left is the proxy for the sign problem. Remember, it's again the same average phase. And remember, if this quantity is close to 0, then there's a bad sign problem. If this if this quantity is around 1, then the sign problem is mild. I can sort of invoke this rebating method that I talked about earlier to overcome the sign problem. And here on the right, I plot the equation of state. So this is density as a function of chemical potential. And you can see that in the same, around the same mu where the sign problem kicks in, I get big error bars, and so the computation, if I don't do anything, just do a standard lattice with rebating, here it's no good. So then I do a particular type of deformation. This is not flow, but I shift the integration contour by a constant amount in complex plane. So this again has the same computational cost as the original calculation because this deformation is done actually on paper. So this again pushes the region that I can reliably compute the equation of state, but then sign problem kicks in, and I start to get these big error bars again. And on top of this, I flow some amount, which is enough to stabilize the sign problem, and I can go way further in the equation of state. One particularly bad limit in terms of sign problem is low temperature, because again, this quantity, it goes to 0 exponentially fast with inverse temperature. And this is, again, the same equation of state. It's, so red being the hottest, blue being the coldest. And at very cold, at the very cold limit, you see this sort of staircase type behavior. So physically, this is quite easy to understand. So at very cold temperatures, I don't have enough thermal energy to excite anything unless the chemical potential is equal to the energy of the lowest sort of excitation, which is in this case the fermion mass. So I create one fermion, and then same thing happens again, and so on and so forth. However, from a path integral perspective, this is a very difficult result to obtain, because so in a path integral, we're sort of averaging over fields and with different weights, and summing this operator evaluated on these different fields, so that and the weights have to be so delicate so that I add a bunch of fields and they cancel each other to a very good accuracy, so that I get 0. So this is sort of, if you think about it, it's a pretty delicate thing. That's why the sign problem is quite bad, because I have to, again, sum many different contributions from many different fields in a sort of a very conspiratorial way, so that at the end of the day, I get 0 for this range of chemical potentials. And it's very promising that the flow machinery actually reproduces such an equation of state. Different limits, continuum limit, thermodynamic limits, again, no problem. So I don't have a lot of time, so I will talk more about the recent progresses. So I'll go very fast with this, but again, this is an example of a gauge theory. So it's a rather simple one. It's a two-dimensional QED, but we can do the same thing. Sign problem is sign problem gets better with more and more flow, denoted here by red, blue, and green, and the equation of state gets better and better. The error bars shrink more and more as we flow more and more. The same thing. The one reason why we study gauge theory is that the sort of properties of the formation of this manifold, the original domain to M, gets a bit more complicated because the field that is, or the space that we're interested in is actually a quotient space, the field space modeled by the gauge group, and there, in certain cases there are some singularities and so on, but in this case they don't seem to cause a problem. That was the upshot of this exercise. The Italian group recently looked at QCD in the limit where the quark masses are very large. So in this limit, basically the theory reduces to an effective theory where the degrees of freedom are Polyakov loops. It still has a sign problem, but it's much easier to simulate compared to actual QCD. So this is a very recent paper, I think it's this year, that there's an exploratory study of the evidence QCD. So in this case, the deformed space is not obtained numerically by computing the flow, but it can be viewed as a particular sum of the fixed points of this flow, which are also called as Lefschetz tymbals, and some fluctuations around these fixed points. But the main idea is sort of similar, and they were able to reproduce the peak of the sort of the Polyakov loop around the phase transition, and this increase in the fermion number density, similar to the plot that I showed earlier, this staircase type behavior. Okay. So there has been a study of the 2D Hubbard model away from half filling on a honeycomb lattice. This is again a fairly recent paper. It was this year. So what they have done is again they looked at the deformation, which is again the sum of the saddle points. So the fixed points of flow is where the gradient of the action vanishes, which are also the saddle points of the action, and fluctuations around those saddle points. And this is such an example of a saddle point on the honeycomb lattice. It's some sort of analog of an instanton. It's kind of nice. And they showed that with this deformation, they compare with the conventional Monte Carlo method with standard rebating, and again deforming the theory to the sum over the tymbals actually improves the average sign. This was again an exploratory study with a relatively small lattice, but again it's promising. There are other proposals for finding such a surface. One of them was dubbed as Lornifolds by the Maryland group. This was around 2017. So the idea is that, computing the flow for every point that's sampled over the Monte Carlo evolution is actually costly. So the idea was to, instead of computing flow for all the field configurations, let the machine learn what the shape of the surface is. And the idea is to give a set of points which are flowed. Initially, they're not created by any Monte Carlo ensemble or anything. They're just a set of pairs, the initial and the final configuration of the flow, and feed it to some neural network, and the outcome will be the parameterization of sort of an approximation to the parameterization of the manifold, and that was cleverly named as the itself a manifold, a Lornifold, and they studied the two-dimensional version of the Turing model that I showed, and the results were actually quite successful. Another idea is to, I don't know what happened to my title here. this is supposed to say sign optimized manifolds. I apologize, I'll fix this. So the idea is similar to the previous one, but instead of trying to approximate what surface that you would get from flow, in this case, the idea is this. So what we're trying to do is to minimize, sorry, to maximize the average phase, so to minimize the sign problem. So let's consider a family of surfaces which are parameterized by some set of variables that I collectively call lambda. And within the set of these alternative domains, find the one which within the set minimizes the sign problem or maximizes the average phase. Again, there are several papers based on this approach, and it also has been quite successful. And in this case, so of course you have to make sure that M is an allowed deformation, but in the examples that were studied, that was done. But this doesn't have to be the manifold that you obtain by flow. So this is this illustrates the sort of the range of possibilities with this approach, that the form domain actually can be chosen in other ways than not necessarily flow. With this, let me just conclude the talk. So you'll recall that I begin with the big sort of motivation, that understanding sort of the phase diagram of QCD, the dynamics, and not necessarily QCD, but there are many interesting, many other interesting, strongly interacting systems. And so this is our peak here. This is where we want to go. We're sort of at the base camp so far. I showed examples of real-time dynamics and finite density systems where this approach works fairly well. And of course, we need many more tools. And whoa, what happened? Hey, okay. We need a lot more tools to bring us to the peak. So I talked a little bit about other deformations. So I gave these two examples, the sign optimized manifolds and to some extent the lornifolds. But one can think of, depending on the particular theory, certain ansatz that can be sort of done on paper that would save a lot of computational cost. There are simulated annealing methods that we're thinking about that can help with sampling the flow manifold. Hybrid Monte Carlo is a good alternative to, again, sample these manifolds. There's technical improvements that have to be done to, again, improve the computational costs. And there are many other alternatives that haven't been fully explored yet. And the final remark I want to make is that all these examples, computations that I showed have been done on mostly my laptop or a computer which is sort of similar. So microphone, I believe. Okay, it's gone. So even the more straightforward methods that I showed have not been tested to their full extent by using more powerful computers. So we still have a long way to go, but we also have a lot of opportunities and tools that needs to be explored and utilized to get us to the peak. So thank you very much, and I would be happy to answer any questions at this point.
Thank you, Gökçe. It was an excellent talk. Judging from this picture, it's not only a far way to that peak, it also seems very cold and hard, and maybe not everybody will survive by the time we get there. But with that, I guess we are open for questions. If anybody has a question, please use the raise the hand. Georgia is always the most active participant. Go ahead, please.
Hi.
Hey, Georgia.
Gökçe, thank you very much for was a really good talk. I have sort of a question, and I have a question in two parts.
Okay.
The first one is, what is the relation between this and what some years ago was called complex Langevin dynamics?
Yes.
If it's the same. And the second question is, are there physical situations where your procedure fails because you cross a pole? And
Okay, so the first question, it is very similar to complex Langevin, but the difference looks, okay, hold on. All right. So the difference is actually quite dramatic. So complex Langevin also solves a flow equation like this. However, it actually extends the original domain to the whole complex plane. So now we're sampling over not a surface which is of same dimensional, but the whole complex plane. So and that results into directions where the action grows sort of unboundedly, because in complex plane there are always directions that you can go where the action increases. So this method by construction so in this method by construction, these flow lines, over these flow lines, the action always remains bounded, or the e to the minus the action always remains bounded. And and we sample a space which is of the same dimension of the original space, not an extended space where which is Cn, which complex Langevin does, but we sampled a mid-dimensional space. So, and that actually changes a lot in terms of hitting singularities and so on. So in this case, for instance, there are no unstable directions whatsoever. So for the second question, I have not encountered a situation where we hit a pole in field space. When there are fermions, there are cases where there are zeros of the determinant, and they sort of might cause numerical problems in terms of creating sort of action barriers and so on. But other than that, I haven't encountered a case where there's a pole.
Okay, the next question is from Kirill Boguslavsky. Please.
Hi, thank you very much for the talk. It was really interesting.
Thank you.
And I have actually a very similar question, but my question is not how it is compared to complex Langevin, but it's more how it is compared to thimble, to Lifshitz thimbles. Because actually it looks like very much similar, yes, but not going to basically time to infinity, where you basically hit the Lifshitz thimble. Do I understand correctly that it's basically the same? Yeah, the same method, but just with some adjustments that you don't go to infinity. And how do you know how long you should go until you get reasonable results?
Yes, very well. Yeah. So yeah, in fact, when I take the flow time to infinity, this surface will become the appropriate sum over the Lefschetz thimbles. So thimbles are fixed points. So when I take the flow time to infinity, so there will be a particular field configuration that flows to a fixed point and stays, and a very small neighborhood around this point will create sort of the thimble, and all the other points will sort of decouple. And so in this case, we don't do that. So this is, you can think M, or sort of the family of m's with different t flows as a parameter of, or a sort of family of surfaces which start from the original cycle and then slowly merge into, slowly sort of approach the Thimble decomposition. There is, I don't know a way to fix the flow time without actually doing the computation and seeing how much the sign problem gets improved, because it's it's a very nonlinear sort of process. The way that the average sign depends on the flow time. So what we have done is just a trial and error. We tried a bunch of different flows, and the one that is the smallest T flow that we can get away with by stabilizing the sign problem was the choice. But I would love to have a more quantitative way of choosing T flow, but at the moment it's mostly trial and error.
Okay, next question is from Vivian and Sarah.
Yeah, thank you. Very, very interesting talk indeed. I was wondering, because we know that at finite density, there are many different phases, and we find that from effective theories of QCD, but with your method, if you have, for example, in the lower dimensional examples you were using, have you considered the effect of your method, or the how good it would be if the theory has some topology? And that's very typical at finite density and in lower dimensional for sure. So how that would be, I mean, do you think your method will work in that case?
Different topology, meaning?
Some topology in the ground state, some, you know, like for example, the method, you emphasize that it would be very helpful for transport properties. But if you have a theory that has non-trivial topology, that would be reflected also in the transport properties. So there would be some anomalous quantities. So how this will work in that case?
Right. So that's a good question. So it would be great if, let's say, so at the level of thimbles, for instance, if I take T flow to infinity, so for different phases with different sort of topologies would correspond to different Thimble decompositions. But on a lattice, that's very hard to determine, because what we have seen empirically is that even if there is not much change in physics as we changed, let's say, the chemical potential, the particular Thimble decomposition that enters into that phase sort of changes with different chemical potentials and so on. So it would be sort of hard to decouple those changes in the Thimble decompositions due to lattice effects and actual physics. So in semi-classics, that's one thing that happens, that if there's such a change, you can see that in semi-classical physics, which is basically which Thimbles that contribute, and presumably in sort of strong coupling, those Thimbles will also get dressed by the contributions from the fluctuations around it and so on. But seeing that on the lattice would be a little tricky. But there are examples, or at least in semi-classics, so you can relate the changes in Thimble decompositions with different phases.
Okay, I don't see any other questions from the audience. I did have a question of my own. Obviously, you didn't solve QCD with the sign problem yet. So my sort of burning question is, what's the biggest obstacle here, and how we can at least approach it?
Oh, yeah. So there are several. Going to larger systems typically requires more flow, and more flow. So more flow is very costly.
When you say larger systems, you mean 3+1 dimensional?
Yeah, larger lattices, higher dimensions. So I've given examples in 2 dimensions. I haven't put it, but we also studied a 4-dimensional system, but with a relatively small lattice. So if you want to go to the continuum limit, the thermodynamic limit, we need bigger lattices, and so that requires either more flow or a better alternative domain, which is perhaps different from what you would get from flow. So that hasn't been explored very well at this point. And the second thing is, which sort of that's one of the things that I want to understand better now, when there's a non-abelian gauge group, the thimbles and actually the critical points so the critical points are singular because you mod by the whole gauge group, and if you look at that sort of modded surface, when the gauge group doesn't act freely, which is the case for non-abelian gauge theories, then there are more singularities that haven't been taken into account by the Picard-Lefschetz theory. So there's an upgrade of Picard-Lefschetz theory, which is called Conley index theory, which should be sort of utilized in this case, I believe, and that hasn't been done yet. So there are conceptual problems due to the gauge symmetry, and there are computational problems as well. So those need to be understood better.
I see. Okay, we have yet another question from Kirill. Go ahead.
Hello, I was very intrigued by your results on real-time on the real-time problems, and my question is a little bit. So it is pretty hard to actually get some numbers or some results from genuine non-equilibrium situations. So when you still are in equilibrium, but you have some time extent, then it seems to be that for instance, stochastic complex non-trivial equations might also get something fruitful. But you seem to also have completely non-equilibrium. Is it, do I understand correctly? And what is the current status for real-time dynamics with this method?
Right. So yeah, what I haven't said here is, so what we did is to discretize the Schwinger-Keldysh action, and then put it on the lattice and do the flow and so on. But the examples that I showed, the examples that I showed here are sort of still with finite temperature. So it's Schwinger-Keldysh with sort of with a fixed temperature. So it is, of course, possible to, instead of having the Boltzmann factor, which is the imaginary part of the Schwinger-Keldysh contour, have some density matrix. So that would be more sort of out of equilibrium. There's some work on that. I should have put this here. Some preliminary work. And one of the things that I am thinking about right now is to put a quench. So there's a sort of a dramatic change in the Hamiltonian at some t, and then see how the system equilibrates back. So I'm still working on it. There's still, I think, some time to obtain actual results, but that would be more along the lines of true non-equilibrium systems, which is doable. It's just requires a little more computational power than what we have right now. That's why I'm sort of hopeful for HMC at the moment.
Thank you.
Okay. It seems like we ran out of questions for now. So thank you very much for the presentation.
Thank you, Igor.
I hope everybody enjoyed the talk. I definitely did. And if you have any other questions, you could always get in touch with Gökçe directly by email. I will be posting the slides. So if you need to review anything, there will be also video posted. So thank you everybody for joining, and thank you, Gökçe, for the presentation.
Thank you.